Chanaji.
Good morning, it's Anthony Butler here. How are you doing?
Hi, good morning, Anthony. Thanks for agreeing to give this talk.
Oh, thank you for having me here. It's just a shame I can't be there in person. I'll just check something for a quick moment.
Sure.
Sorry about that. So I presume you just want me to share my screen with the presentation on? Is that the way it works?
Yes, so we can see if it works now.
Right. So share screen, desktop 1, share, and you've probably got a whole presentation, the whole desktop at the moment.
Yes.
And if I go to view presentation mode, hopefully now you've just got the PowerPoint.
Yes.
Great.
It works.
Just try a few. So where in India are you at the moment?
Hello, Chitra-san, can you hear me?
Yeah, Archana ji, welcome.
Hello.
Yeah, we can hear you.
I can hear you.
I think these people are out for lunch. Anybody there?
No, we can hear you.
DAE?
We can hear you. Can you hear us?
Anthony, can you hear me?
Yes, I can hear you.
I think she can't hear.
Ah, but I can't hear you. Oh. So maybe I should just leave and come back again. All right, just give me 1 second.
Yeah, Anthony. So I was telling we are in the eastern part of India, state of Odisha.
Right, I have to say I'm very disappointed that I can't be there in person for this conference. India is a country I've visited on holidays 4 times and work once, and it's always an exciting trip.
Where all did you go?
I spent about 6 months in India. So my first trip when I was 20, we went Delhi and then Rajasthan, Himalayas, and then down to Goa. And then my second trip, my wife and I actually traveled from Bangladesh across to Pakistan. So we went through northern India, the Himalayas, and then Punjab and across from Amritsar.
Hello?
Yeah, Archana ji, can you hear us?
Okay, I think there is some issue in the audio. So without losing any time, I think we can get started. Vedant, is that okay?
Yes. I don't know how. Yes.
Okay,
right.
Good. Thank you. So we come to this wonderful session on detector development and societal applications at the 24th DAE-BRNS High Energy Physics Symposium. We just heard yesterday from the CERN DG that industries based on physics and mega science projects generate over 17% of turnover in Europe. And I think this is an aspiration for India. And this session is certainly going to seed many ideas in our community. So without much ado, let's go to this sensational pictures that have been making the rounds of the net and the whole world, in fact, and listen to Dr. Anthony Butler, who has been the pioneer and originator, so to speak, of this imaging, 3D imaging of the body in medical diagnostics. So Dr. Anthony Butler, please take over while I fix my audio. Thank you.
Well, thank you for having me here. And as I was just saying, it's rather sad that I can't be there in person because I always enjoy visiting India. I always particularly like the people, but the history and the food are amazing as well. So instead, you get to have me sitting in my lounge talking about one of my hobbies, which is medical imaging with high energy physics detectors. I've entitled this talk From the Higgs Boson to Molecular Radiology. What I'm going to do is talk about the history of how our technology developed, and although the introduction put some credit towards me, it really is like most things in science, dozens or hundreds of people's over many years, and so I'd like to touch on some of that. I'm also presenting on behalf of our team. We have about 50 people here in New Zealand, all of whom have been contributing, so really I am the spokesperson. I've got a number of academic affiliations. I'm at CERN, I'm in the PH department where I'm part of the Mesopix Collaboration and the CMS Collaboration. I'm also at the University of Canterbury where I'm a professor of physics, and at the University of Otago where I'm a professor of radiology. And I really ought to introduce my father, that's his hand there, with a hacksaw approaching it. So I've been working with him on this project since about 2005 when we first started. He's the New Zealand representative for CMS. So he's been a particle physicist for decades and a mathematical physicist before that. My talk's divided into various parts. Firstly, I'll talk about our goal and our motivation. Then I'll talk a little bit about the history of CERN and new detectors and color X-rays. And then I'll talk about the scanners we built, some medical applications, and briefly an outlook for the future. So what am I talking about when I say black and white to color? Well, X-rays, Röntgen discovered the first, or imaged the first hand in 1895. Around 2006, we were also imaging hands, in that case, fetal hands. Back when Röntgen did it, he just measured the total number of X-rays. By 2006, using photon counting detectors, we were able to separate out the photons into different energies, frequencies, or wavelengths. And that allowed us to start measuring that bone has a different spectral profile than soft tissue. This was known, it just wasn't easy to measure. So we think of ourselves as moving from black and white to color, or from energy integrating detectors through to spectroscopic detectors. So what do I mean by spectral CT? Well, this is a standard diagram of a CT. On the top half, we have an X-ray source, which puts out normally an X-ray tube, puts out a range of frequencies or wavelengths. They're attenuated by the object. In a hospital, we call that a person. And then they're, in a traditional X-ray system, they had an energy integrating detector giving you an anatomical image. So you lose all of the mass attenuation profile or the linear attenuation profile. Our system, we use a standard X-ray source, again, putting out different frequencies and wavelengths, and then they're attenuated, and then we use a photon counting detector with multiple thresholds to identify many points on the mass attenuation curves of the various components. So it's moving from black and white to spectral. CT systems, some of you will be familiar with these. Basically, they're just a way of taking a 3D picture using a 2D source. So you have an X-ray source, an array of detectors that rotate around the person or the object, and that builds up a 3D picture. The picture on the right is a standard image from our hospital. The person has lung cancer. They've got a large mass obstructing here. You can see that this is through their chest. You can see their bones are white because they attenuate a lot. The soft tissues are kind of gray. The fats are lighter gray. And in fact, in their blood vessels, they've had iodine injected with standard contrast used in most CT scans, and that's showing up white because it's highly attenuating because of its K-edge. So how common are these things? Well, roughly, there are about 300 million medical CTs taken every year around the world. So it's an awful lot of people who undergo this procedure each year. It's about a 47 US billion market, and it's used everywhere. So CT is used for joint injuries, fractures, bones, implants, cancer diagnosis and management, heart disease, stroke, and infections. So where did this all begin? Well, as I said, I'm a member of CMS, and so is my father. This is a picture of him again here. Here's CERN. You guys are probably well familiar with it. There's the campus there. the accelerator going around the outside. And at this point over here, there's the CMS detector. This is actually taken about 15 years ago when it was still above ground. And in the middle of that is the pixel barrel, or the tracker as it's sometimes referred, which is using photon counting detectors. So where did photon counting come from? Well, right back in the late 70s, early 80s, three physicists started looking at new ways of measuring particles. Eric Heine is one that I've had the good fortune to know about and work with. And he was one of the people who developed the first silicon microstrip detectors. So that was late 70s, early 80s. The purpose was for high energy physics, but it very quickly became apparent that you could use them for other particles. So in the mid-90s, a group of scientists at CERN and the collaborating universities formed what was called the Mesopix Collaboration. Originally, there was only 4 universities. We're now up to Mesopix 4. There's all up about 40 universities involved. This picture was taken probably around 2010, where we had a collaboration meeting in Prague. And as you can see, there's about 50 people attended, maybe a few more. And all of them were engineers and physicists trying to take photon counting into medical applications. This is a detector we use in our scanner at the moment. So it's a standard hybrid pixel detector. So the active area is 14 by 14 millimeters. In each pixel, there's about 4,500 transistors, a digital component and an analog component that allows us to split the X-ray beam up into about 8 colors. It's working one photon at a time, and actually there's some very clever bits about it in that every pixel communicates with its neighbors. So CERN actually was, as I said, started the work in the mid-90s. By 2011, there were a number of groups around the world looking at photon counting and spectral imaging. So Michael Campbell, myself, and some other scientists got together and held workshops, and we now hold it every 2 years on spectral applications in medicine. In this particular example, which is a Mars image, we had a mouse where we had iodine contrast, gold contrast, it might have been barium contrast, and calcium in the bones, and we measured the X-ray color to separate the components. Philips was doing the same sort of thing. This is a mouse with 2 contrast agents in the animal, and GE had a 2-energy system that they could use on, they could take images of people even if it was only one slice. So that was way back in 2011. By 2019, things had evolved. This is one of the images. It's actually my father's wrist again, this time showing his bones and his watch. We were measuring 4 to 8 energies. Siemens was working with the Mayo Clinic using a 2-energy system, and then Philips were in the process of building a human system. So the field was evolving very, very rapidly. At our first workshop, we had around 40 or 50 people, and now we only accept up to the first 120, and everyone has to put in an abstract. So it's a nice scientific community that CERN has been supporting. Here's our last collaboration or workshop meeting. And actually one of the things that really struck me is I had to do the summary talk, and so I was taking quotes from various people. Stefan Kapler, who's a scientist on the committee, said, "This is what happens when you bring people with good ideas together to form a community." And I have to say he's right. By having a number of scientists around the world all thinking about how do we do this? How do we take the field forward? How do we help those 100 million people a year having CTs? It's been really nice to advance. So where's the detector technology going? We're in the late stages of the design with, soon the Mesopix 4 collaboration, and the late stages of design for Mesopix 4 should allow up to 12 energies with 4-side buttable for large area, and about 5 to 10 times faster than traditional or the current photon counting detectors. And then there's the TimePicks family of detectors. These are event-driven detectors. So instead of reading out a frame like a camera, it reads out 1 photon at a time, and it reads out the time over threshold in each pixel, and then offline you do a reconstruction of the spectrum, and this is an image from Rafa Bellabriga, one of the chip designers, and he's been able to show that if this is a circuit board, 256 by 256 pixels, he's been able to measure the full spectrum from the transmission X-ray. So you can see he's divided the spectrum up into about 25 different bins. So it's a really very advanced technology, especially when you compare it to what's state of the art in the hospitals, which is pixels of 1 millimeter that glowed the more X-rays that hit them. So what's our team been doing? So as I said, we have a system we call Mars. It sounds nice and futuristic, and we've been building scanners. We're a collaboration between 4 New Zealand universities, and we have a whole bunch of partners around the world, ranging from Rensselaer Polytech in New York, Chinese University of Hong Kong. We work with Lausanne Hospital and many, many others. So here are our universities. We won some innovation awards from our local government about best product, best innovative business, etc. This is the first scanner we shipped to a biomedical researcher. It went to the Notre Dame Imaging Lab. So the scanner used to look like, this is the older systems, used to look like a barbecue. You lift the lid up, you put your specimen in, and we had a 3D workstation for analyzing the data. At this stage, we were working with CZT, cadmium zinc telluride, a room temperature semiconductor, as a sense material, and that allows us to go up to 120 kVp on our tubes, and that's enough to get through a patient. We had continuous motion spiral scans, modular readout, automated all the detector setup, and the group was growing. We were actually, this is only the people who assembled the scanner, we were about 20 people at that stage. So we had a mathematician, a whole bunch of engineers, and my father there looking a bit like me. We're in the same coloured shirt. And then we built ourselves a human scanner for research. So this is an open bore CT. So you put your object in through there. The bore of the scanner from there to there is about 70 centimeters. So you can get shoulders in if you need to. You can bolt on and off the X-ray tube. The detector's on the other side. This is the first scan that we did. So actually I took it off my father. There he's got the standard model on his back, being a particle physicist, and there's his foot being scanned. These are the scanners we're now producing. So this is looks like a pencil sharpener, but it's compact, it's shielded, and it's designed for actually taking it out into the community. So instead of having CT scanners that are in hospitals, this scanner, which is a wrist scanner, can be taken out and put in a GP practice, an orthopedic surgeons, or an emergency department. So what have we been looking at? So I'm just going to show some biomedical results from around the world. This is our collaboration partners. So this is a workshop we held in 2018, pre-COVID, when we could actually bring in people from Notre Dame and Germany and Russia, US. And these were people who were using our scanners for identifying applications in medicine. This is one of the earlier pictures. This is a mouse which we've injected with gold, gadolinium, and barium. And we've used the X-ray spectra to separate out the water, which we've color-coded blue. Calcium we color-coded as white. Iodine in the kidneys and the bladder, we've done that as red. There was gadolinium that we put in the bowel, and we put gold into the lungs. So instead of a standard grayscale image, we've used the X-ray energy to identify which material's which. So that tells us that's iodine. It's definitely iodine because it's got the right spectral characteristics. So what have we looked at with this? So this is looking at atheroma, so heart disease and stroke. So this is the image on the right here, is a vertical slice through someone who's had a stroke. So I don't know if you can see my camera as well as my presentation, but it's a slice sort of up and down through the head. And there are 2 large blood vessels, one there and one there, that go to the brain. And in a stroke, these often get blocked off. You can see it's very, very narrow. It's white because there's iodine in it. This person then came in with a stroke, and then they would have had an operation, and we take that specimen out. So we've taken out that narrow bit of vessel, and then we've scanned it. And if we scan it, we can actually see the difference between the fatty core and the watery parts of the plaque. So this fatty part, is it full of lipids? It tends to be full of foam cells, and that's a sign that this plaque is very unstable. We can identify the calcium as large, lumpy bits in this plaque, and that actually corresponds to that bit of white there. So at 100 micron, the thickness of a human hair, we're able to see not just the shape of the plaque, but the contents of the plaque. We went on, and this particular plaque, this person had a bleed into it. So this is, again, the blood vessel that's come out from an operation. And they're very lucky they had this one taken out just at the start of their stroke, because that bleed into it there will have been narrowing the vessel. And when we scanned it, we can differentiate the calcium from the iron. On a traditional CT scanner, both of those will show up as white. For us to here, it shows up as iron. We measure that spectral characteristic. We work with Oregon University, Oregon Health Sciences, and here's a femoral neck. So this is the part of your bone that goes into your hip. So it's come out of a cadaver, a patient who died, and we scanned it, and we get very, very high resolution. If you look on the right here, this is just integrating all the energies. It looks like a standard CT, but we can see the microstructure of the bone. So we're seeing things at 100 micron. But in addition, we get a calcium map, a water map, and a lipid map. So we know in some diseases like osteoporosis, the calcium map will change, even though the structural elements will remain the same. Sometimes in a fracture, the amount of water will go up. You can get diseases which will change the amount of lipid. So in a single scan, you get structural or anatomical information, but you get compositional information as well. We also are able to remove many artifacts. So in this situation here, this is a sheep clavicle, and we've got a plate and screw. So plate and screws like this are often used when people break bones. One of the problems is the metal interferes with the CT scan. It produces a lot of artifact. That artifact actually comes from the change in spectrum introduced by the metal. So in this instance, we're able to identify it as metal, and we color coded it green. And because we're able to identify it as metal, we can actually remove the artifact. So we can see the thread on the screws very clearly as they've gone into the bone. And I've got some pictures later on which compare that to standard imaging, where you just don't see the thread. There's too much artifact. This is a crystal arthropathy, so gout and pseudo-gout. This person had their finger amputated because they had so much pain from their gout. We did a scan on a dual energy system, and you can start to see some of the tophi. Dual energy systems work by flashing the X-ray tube between two voltages. Putting it on a multi-energy photon counting scanner, this is the same finger, we get far higher detail and far more confidence that the crystal type. So we're actually identifying the CPPD crystals that are causing this person's disease. We've looked at osteoarthritis. So this is someone's knees. This is a healthy knee joint. There's space between the bones. This person with osteoarthritis, it's all narrowed. What happens is the cartilage wears away. So if we look at this person's had an operation, had this cartilage taken out, and we've looked at the medial and lateral strips, left and right side, and we've introduced a contrast agent called gadolinium, and that diffuses through the cartilage. So this is images of the cartilage. So these correspond to these strips of cartilage through here. And we've measured the gadolinium contrast agent. And in this particular sample, we can see in sample 6.1, the gadolinium's infused through quite rapidly. And we know from biochemical analysis that where that happens, you're missing glycosaminoglycan. So that area there has a biochemical change that we can see on a scanner, despite the fact the cartilage is still normal thickness. So to summarize that, in people who have osteoarthritis, we're able to measure the biochemical change before there's joint wear. And that means that it's possible to start thinking about things like earlier treatment for diseases, because we can measure the biochemistry early. This is some work we did with Maryland University. In this particular instance, they've got a nanoprobe, so that's about 10 nanometers across. The core of that is hafnium oxide. The hafnium has a very specific spectral signature, but it's got a K edge in about the 55 range, I think. And the nanoprobe on the outside has targets microfractures in bone. So in this particular, start with the image on the right, this is a rat where they opened up the rat's leg, did an operation, scraped the bone, closed the animal up, and then injected the nanoparticle via the tailbone vein, and the nanoparticle has targeted the area of bone damage, which is to say that we now have a way to measure bone metabolism on an X-ray system. So normally you'd have to have a PET scanner or some other form of nuclear medicine to measure bone turnover. Here we're doing it on a CT system. Again, another excised human finger. In this case, they damaged the bone and they incubated the nanoprobe with the finger and the nanoprobe attached to where the bone damage was. We've been looking at cancer. So this is some work done at my university at Otago Medical School, and this is in Notre Dame University. In both cases, we've been looking at breast cancer. Start with the case on the left. So these are cell pellets. So these are falcon tubes, small tubes full of tissue cultures. In this tissue culture, we had a cell line with the HER2 surface antigen, and we used a Herceptin nanoprobe. So that's a monoclonal antibody attached to a nanoprobe, and it lights up that cell line. We did a crossover study where we used a different monoclonal called rituximab, and it doesn't light it up. So a nanoparticle attached to this cell line, and this particular well of the plate, there was a different monoclonal, didn't light up. So that's strong evidence that we're able to light up a single cell line within cancers. Here, this is a mouse model. So this, you can picture the mouse. What they do is they implant the cancer under the flank of the animal. So they've done an operation, injected a few cells actually onto both sides. And being breast cancer, it has microcalcifications, and he's used a bisphosphonate nanoprobe, showing up red here, where his nanoprobe attaches to the microcalcifications. So again, we've used the spectral nature of X-rays on the left to label a cell line, and on the right to label another part of the breast cancer disease. And in fact, we can use these two methods in combination. So we can now image breast cancers, at least in the laboratory, looking at two different molecular markers of the disease. So we're taking the imaging from anatomical to molecular. So we've also started doing some human research. I showed our large bore scanner earlier, and I showed a picture of my father's foot going in. This was the foot. If we just look at a single energy bin, a narrow energy bin, it looks very much like a standard CT scanner, but we can separate out into the water component, the lipid component, and the calcium component. If we look at what that means in a radiological sense, we've got the cortex and trabeculum at 80 microns. So we've got very, very fine structure. We've got the bone mineralization, that's the calcium maps, and that's in the quantitative, as in milligrams per mil. So we don't say it's got more or less calcium, we actually quantify it as partial density. And we can see the soft tissues, we can see the ligaments and the tendons very clearly in the ankle. So to compare it with other modalities, this is what a standard CT of a foot looks like. This is what a standard MRI of a foot looks like. And as we've done in this case, we pulled out the calcium map, a fat map, and a water map. So I tend to think of spectral imaging a little bit more like MRI. Off a single study, you're getting multiple channels of information. When we first released these images, we actually were pretty excited. We got this one of the wrist, was seen by millions of people on Twitter, and this was picked up all around the world, which I found really exciting. It was really nice to show that the work that had been done at CERN in the 80s, 90s, and early 2000s was finally making its way into medicine. So let's look at an actual real patient. So this person had a scaphoid injury. So I'll explain what that means in a minute. It's a 25-year-old male. He was working in the mining industry in Australia, and he went on holiday in Switzerland. As a miner in Australia, they tend to earn quite a lot of money, hence he got a holiday in Switzerland. He's got a degree in geology, and he worked out there doing fairly physically tough work, but as a geophysicist, earning good pay. About 1 o'clock in the morning, he fell over. He was a bit uncertain about exactly what happened. He developed wrist pain and went to the emergency department, where he had plain radiographs taken. And about 10 days later, he returned to New Zealand and he still had pain in the wrist. What in fact happened is he had fractured one of the bones in his wrist. I don't know if you can see my hand, but it's the one at your base of your thumb. And it's unfortunately really common. About 15% of these injuries are missed at their first presentation. So people fall over, they go to their doctor, they have some x-rays done, and you still miss 15% of the injuries. And it's quite an important injury because the blood supply, when it's fractured, when it's broken, you can cut off the blood supply and the bone will die. And it's very, very hard to heal once it happens. So that's what happened to this guy. So he had a screw inserted into his bone in January, had ongoing pain, didn't get better. So he ended up having multiple CTs and multiple radiographs. And at 4 months, we imaged his wrist on our scanner, and then he had another operation. So this is why I say this is important. He was off work for 6 months. So he went from a high-paying job to living off insurance money because he couldn't work. He had lost the quality of life, and often for people with wrist injuries, that means they can't write with a pen, might be hard to type, they may not be able to drive their car. He'd had 2 surgeries and multiple investigations. So what might seem like an innocuous injury, falling over and hurting your wrist, can be very, very dramatic for the patient and cost a lot of money. So the surgeon in this case wanted to confirm the fracture, assess the union or how well the bone is joining back together, whether it was fully complete, partially complete, or not going back together. And to do that, we need to measure the calcium, the lipid, and the water around the joint, around the fracture. We need surgical planning, so you need bone alignment, bone quality, fragmentation, and cysts. So ideally, you need that at very, very high resolution, particularly the bone quality measurements. And you want to look at the soft tissues and ligaments. Did they do some other injury? After an operation, you want to look where the screw is, whether it's moved. You need to look at the implant changes, infection, and bone resorption. And you need to look for callus formation, that's bone healing. So this is the person's wrist. It was a 120 kV scan, took about 22 minutes. The effective dose, so that's the equivalent of, I guess it's an estimate of risk. It's the microsievert range. So that makes it about 12 hours of background radiation. So about the same as a long haul flight. If we just look at a single energy channel, it's very high resolution, much higher. I'll show you some the ordinary CTs. You can see the bone structure, the internal structure, and you can see the screw. Here we're just displaying the water and calcium channels. So the water shows the tissue, and you can see the bone. If we look more clearly on where we show the calcium, lipid, and water, there's the screw. This is a scaphoid bone where my pen is going round, my pointer is going round, and that's the one he broke. And we get pretty reasonable data. Again, another 3D view, the calcium, the water, and the lipid showing where the screw is. So let's compare it to standard imaging. So as I said, just looking at our images, we get 90 micron voxels, so we can see the internal structure of the bone. We did exactly the same images on a standard CT. So this is a CT that you might have at your local hospital or radiology practice. And at best, they have 300 micron voxels. So the ability to look at the quality of the bone there in the scaphoid is significantly reduced. The surgeon wants to know, is the bone good? Because they're about to put a screw into it. So they will need to know if the bone will fall apart. We've got much better views of that. At that scale, we start to be able to see other things. So just near the screw, we can see a small defect in the surface of the joint. That was where the surgeon said he accidentally damaged it. And so we get really good views of the bone morphology. We can see the bone is fragmenting and falling apart through that fracture. That's a scaphoid in one view. And so the bone's actually starting to turn into little speckles of calcium. A really important question is when the screw goes in, is the screw holding? What's that bone metal interface like? On a standard CT, you get this artifact around it. I was talking about it before. So that black line around the screw is a problem that you'll get in all standard CTs to a greater or lesser extent. It's called beam hardening artifact, and it means you can't tell how well the bone and the screw are integrating. Here's another view of it. So you've got that lucency around it. Whereas on a spectral scanner, you measure that artifact and you can remove it. So we can see really nicely that the bone and the metal are integrating. We can start to measure the bone density. So just a single one for comparison. This is the lunate bone. This is this one over here. This is completely normal. And so that's a normal amount of calcium you'd have in this bone. The proximal pole, this is this part of the screw here, the bone here, is very, very high in calcium, way beyond what it should do. And that bit of bone is dead. So it's, instead of healing normally and laying down normal bone, it's just turning to a solid lump of non-functioning dead bone. The faraway point has a moderate amount of calcium. This is a distal pole through here. So it's healing. It's not returned to normal yet, but it's not laying down abnormal calcium. And in the middle, through the scaphe, through the waist, which is that part through there, the calcium is lower than expected, but it's still there, so it is probably going to heal. We also looked at some of the more subtle regions. So in here, we've got this is the standard image. If we look at the various maps, we've got lipid and water in the bone, and that lipid is probably, we're not sure, related to that bone dying off through there. So we can actually quantify there's a little lump of lipid in there, a little bit of fat. So in this particular case, where could our scanner have helped this patient? Well, we might have prevented that initial misdiagnosis. As I said, 15% of injuries are missed on plain films. Had he had a proper 3D high-resolution scan in the clinic, we might have prevented the whole saga of his missed fracture. And as I said, our scan is designed to fit in ED departments. It's designed to be where the patient is. When the pain doesn't settle in 2 weeks, he would have been at the orthopedic surgeon's office. That's another place you could actually put up one of our portable scanners. If you compare that to MRI, MRI requires large rooms, typically sort of 70 or 80 square meters of floor space. They require liquid helium cooled superconducting magnets, 3 technicians to run it. And that's just a standard MR, whereas our scanner can be put in the surgeon's office or the emergency department. Post-op, we've got much, much better imaging in the presence of metal. I showed you how it compares on CT. If you try and image metal on MRI, it distorts the background magnetic field. You don't get anything. We get really good bone metal interface, and we've been able to assess the healing of the bone. So in this one case, we've been able to, there's 3 points where the improved imaging would have significantly improved his healthcare. So I'm going to just wrap up now, and hopefully that's about the right length of time. I guess this is the main message of my talk. There's a direct line from the high energy physics research through to improvements of healthcare. It's taken, depending on when you begin and end, anywhere between 30 and 40 years over that whole journey, from Eric and his friends thinking about silicon strip detectors through to first human experiments. And there are hundreds and hundreds of people involved. But I think it's really important to recognize, had the fundamental research not been done, had the technologies not been done, these changes to healthcare simply wouldn't have happened. So I'm going to stop sharing my screen, and I'd love to have some questions. I know it's very hard in this format, but I'll be delighted to take some questions.
Thank you very much, Anthony. This was a mesmerizing talk. I'm sure that there will be many, many questions. I request the participants to please raise hands, and I will go through those questions. Thank you very much for this wonderful talk. Vivek.
Hello. I have 2 small questions. One is, with the CZT detector, do you expect the exposure to be much smaller than the ones that you get when you normally go to and get your X-ray done on a film? How much better would it be, the exposure? How much lower the exposure?
The CZT has an efficiency of about 100% at 100 kV and about 80% at 120 kV. Whereas a standard X-ray is also 100% at 100 kV. So our ability to stop the X-rays is about the same, convert them to signal. Where the benefit comes from is that with photon counting, we get rid of the electronic noise. And so you get a much cleaner signal. So yes, I expect the dose to be lower. I quoted it halfway through that on our big scanner. We have it use about half the number of photons that a standard CT would use. We've actually focused not on reducing the X-ray dose, but increasing the information. Because if you're dividing the spectrum up and doing it in more analysis and doing much higher resolution, you need more photons. So we've said, let's keep the photon number about the same and provide more information. There are people out there who are focusing on reducing the dose as low as possible, but they're sacrificing information to do that.
Okay. The other small question is, can this technique be also used in, let's say, archaeology or in artifacts such as painting and so on?
Absolutely. So within the Mesopix Collaboration, people are looking at different applications. There's a group in Prague called the Czech Technical University and a local company called Advocam, who have been using the spectral imaging for analysis of paintings, 2D paintings, because a lot of the old paints have metals in them. And so you can measure the metals. And in fact, they've got one example. There's a YouTube video where they're able to measure the painting underneath the original paint, or underneath that have been used. We personally looked at a few historical artifacts. I know that the group in Hong Kong University have been, I don't know if they published it yet, but they've been certainly looking at some Chinese artifacts, historical artifacts. In New Zealand, we don't have a lot of historical artifacts, so we don't do so much of it.
Okay. Thank you very much for the excellent talk.
For other questions, I do not see hands here. Please don't hesitate. This is an opportunity. If not, then may I ask you a question or two? One is about the status of TimePicks. Would you like to tell us where we stand in terms of commercialization with the TimePicks and the latest versions, so to speak?
Well, TimePicks 3 is well and truly commercialized. There's a number of companies using that. I'm probably not the right person to say what they're all doing, but you can Google the web and find TimePicks 3 being used all over the place. TimePicks 4 is being used by the collaboration members and hasn't been commercialized yet. It's still very much in the research phase.
Very good. So is it Nikef leading there, or which?
Nikef has been very involved with TimePicks. They're not actually leading the commercialization. There's a company down the road called Panalytical, and I believe they're using TimePicks and XRF, which Panalytical was spun out of Nikef.
Okay, thank you. And I mean, I just wanted to mention that it took about 30 years to get here, so to speak. You know, and I think that for the younger members in the audience, they should not take all that time, rather grab all the experience, and then we can shorten this 30 years into a much smaller time.
Yeah, so, I think that's right. I tried to sort of present that in my talk, that actually there's a huge line of work and hundreds of people involved. And so everyone contributing together actually is how you get there. And if it had been one or two people doing it, it never would have happened, but it would have been generations to get there.
Well, thank you very much once again. There is another question. Yes.
If you permit. No, I wanted to ask, what is the cost of this device? Can it be afforded by, orthopedic surgeons, private orthopedic surgeons and so on in India? And from that point of view, I'm asking this.
Short answer is yes. The scanners are not significantly different in price from traditional CT scanners. It's sort of hard to put a price on medical equipment, because at the bottom of the range, you've got a 2D X-ray, which might cost 100,000 US or even less, whereas an MRI scanner costs millions of dollars and has 3 people to run it. So we're at the low end of the price. And actually, we have a company called Genetics who operate out of Delhi, who distribute our equipment in India. So, but if you email me, I'm sure my address must be around. I can send the link to Genetics, and I'd be very happy to talk to you.
There's another question, please. Anthony.
Yeah.
Amolji, you
Yeah.
have a question?
Yeah.
Thank
So
you.
you showed the detection of some of the, especially metals and compounds. You showed gold, gadolinium, and iodine and water. Is there a specific class of elements and compounds that are amenable to such imaging where you can distinctly see them?
Yes, so I divided the materials into two categories. The first, what I'll loosely call heavy atoms. So anything where the K attenuation edge is in the diagnostic X-ray range. So iodine has a K edge of about 33, gold has a K edge of 85 or something. And so anything between iodine and gold on the periodic table is really easy to see. It sort of lights up like a fluorescent, well, not fluorescent, it's very, very easy to see. The lighter elements, like calcium and iron, are much harder because they're closer on the periodic table. You've really only got some subtle differences in photoelectric and Compton effect and some second order effects. So that's why we were so pleased when we could separate calcium and iron within the atheroma plaque. There's a group out of Canada led by Hugo Bouchard, who's a medical physicist, and he's demonstrated on our scanners, he's published in Medical Physics, showing that he could distinguish different types of plastics. But it was basically looking at all the light elements, looking at how much carbon, oxygen, nitrogen is in the various compounds, and classifying it into about 8 different types. So that's a harder problem. The contrast agents that I showed, hafnium, gadolinium, gold, they're really simple. And so if you're going to inject something, that's what you choose to inject.
Okay. So thank you very much for that answer. And I think we have lots more to discuss. Nevertheless, given the challenge of keeping time, I'm sorry that I have to move on now, unless there's another question. If not, then let's thank you once again from all the participants. In this format, is not easy to give a good applause, but thank you very much. So we move on now to the next speaker. And our next speaker is Professor Juan Gomez Cadenas from Valencia. And he will speak to us about the television of particle physics, where everyone can just sit glued looking at the various images that come out. And that's the time projection chamber invented by Dave Nygren about 50 years ago, if I'm right. So I think without much ado, let's look into this wonderful device and what it can do for physics and what it can do for society. Professor Juan Jose.
Hello, good morning, everybody. It's a pleasure to be here. Let me share the screen and show you my transparencies. Let me see. Can you see my transparencies?
Yes, we can.
So let me start by telling you that contrary to, let me just move in the format, I need to move this thing a little bit where it doesn't bother me. All right, so contrary to what the name suggests, time projection chambers, and to popular belief, as Dave Nygren once told me, the main purpose of time projection chambers is not time travel. Actually, there are numerous devices which have been invented to move people and stuff around in time. And you can see in this transparency that there are plenty of time machines around. The only problem is that none of these time machines, unlike Nygren's TPC, is known to work yet. But now, the real-time projection chamber was invented by Dave Nygren at the Lawrence Berkeley Laboratory in the late 1970s. And the first application, you can see in the left plot, you can see in this plot on the left, a very young Dave Nygren talking to another colleague in the hall of the PEP detector, PEP4 detector. It was a plus-minus collision, and it was used to study electron-positron collision at 29 GeV at SLAC. By the way, a few years later, I worked there as a postdoctoral student. So after the first application of the TPC in PEP, there was applications in Tristan Collider at the KK laboratory, then in LEP, And then, so basically TPCs were known to work everywhere you had E plus, E minus collisions, but then the thing expanded to heavy ion studies and also actually to LHC experiments. So TPCs are all over the way. They have become one of the most successful devices in particle physics. And this is the original PEP4 TPC. It was already a very modern TPC in spite of the fact that it's close into 50 years old. The main idea of a TPC is that you ionize the gas and then drift for very long distances the ionization electrons. You read the ionization electrons in the anodes, and normally what you do is you segment the anode and you can get the position on XY from this segmentation. You get the longitudinal position by trading time, which you measure from the drift time by position. And in particular, in the PEP4 TPC, you could also measure in wires the ionization. So you could measure DEDX and get a very good measurement of particle ionization and therefore particle identification. The TPC, the original PEP4 TPC, was pretty long, 2 meters long, 2 meters diameter. This will be relevant for what I have to tell you later. And it operated at a reasonable pressure of 8.5 bar with a cathode voltage of minus 75 kilovolts. So it was already a huge achievement already for the time. Now, since that TPC, as I said, they have expanded a lot over the place. Here you have an incredible example of what you can do with TPCs. This is the picture of tracks emanating from heavy ion collisions in the STAR experiment at RIC. And this is 200 GeV per nucleon. And as you can see, there is a zillion tracks coming out here. And each one of those tracks are being tracked by the TPC. But in the other extreme of the equation, you can use TPCs to make very detailed picture of single rare events. What I'm giving you here is an example that will become relevant later. These are electron tracks propagating in high pressure xenon gas. And the left plot corresponds to 2 electrons. This is the signal that you're going to have if you ever see a neutrino-less double beta decay, or even actually a normal double beta decay. It will produce you 2 electrons in the chamber and nothing else. Because you are at high pressure, what you can see here is like this little spaghetti turning around is totally dominated by multiple scattering. So by looking at the vertex, you cannot really tell there are 2 electrons there. But you can see the energy, the positions at the ends of both tracks, and this tells you that there is indeed this kind of a spaghetti with 2 meatballs is 2 electrons, while the background that comes from radioactive decays are typically single electrons, and this single electron has only 1 ionization ball at the end of the track. So by making this very detailed picture of those electrons, TPCs are able to give you electronic pictures of rare events. And this is like the opposite, or almost the complementary application to what we saw before. So TPCs have been central to major discoveries, and the Higgs is of course one example. You can see here the picture, pretty pictures from Atlas and CMS, and every track being tracked by the beautiful TPCs. But for my talk, what is important is that I do believe that TPCs may be fundamental for new discoveries. So any new discovery is by definition a unicorn. You don't know what is it yet. You may think you know, but as I will try to demonstrate later, the most interesting thing about rare searches events is what you don't know that you don't know. So this plot tells you actually that TPCs are at almost 50, they're fashionable as ever. And since 2000, we get more and more and more applications to dark matter, to neutrino-less double beta decay, to nuclear physics, and to all kinds of rare searches of TPCs. So let me give you a couple of examples. The first example is the search for dark matter. Here is a classical picture of the bullet cluster, where you can see these 2 clusters of galaxies passing one through each other. And the gas, the heated gas in the center of the galaxies is glowing there, sending us X-rays. It's telling us here's where most of the mass, of the visible mass, should be. But the gravitational bending is not there. It's not where the gas is, but where the stars are. So this is telling us that there is a lot of unseen matter, which is matching and gravitationally pulling together with the visible matter with the stars. We don't know what this dark matter is, but we know for sure that this matter is there. And people, in particular particle physicists, have been searching for a few decades already what kind of animal, what kind of unicorn this dark matter could be. So let's move on to liquid xenon or Xenon TPCs for that matter. Now, why xenon and why liquid xenon TPCs? So let's first think about what kind of searches we want to do. Let's start by thinking in what I will in a second call our noun unknown. So our noun unknown is the thing our favorite hypothesis about something we don't know. So about dark matter, our favorite hypothesis is that it could be made of weak interacting massive particles or WIMPs. And such WIMPs are a sort of heavy neutrinos. They are sitting around there. They almost don't interact with matter. When our planet goes around the sun, it crosses all these WIMPs, and there is a wind of WIMPs which are interacting against everything, essentially not interacting against everything. And one of them eventually can hit our detectors. Now, one interesting thing is that the cross-section of the WIMPs is proportional to the atomic number square of the material it hits. So we would like to make detectors which are made of heavy A detectors. And in that sense, liquid xenon is fantastic because it's pretty heavy. So it will do. Now, the other thing is that when these interactions, this rare interaction occurs, we don't have an external trigger to tell us that it has occurred. We don't have an external beam like the PEP4 guys had. So we need a way of self-triggering the detector. Now, xenon has the beautiful property that it scintillates naturally. So when there is an interaction in xenon, there will be primary scintillation. And this primary scintillation can be recorded with optical detectors, for instance, with photomultipliers, as you can see in the picture. And it marks the start of the event, T0, right? So after this original scintillation, we will have some primary ionization. And by the way, we need to be as low threshold as possible because we expect very little energy to be deposited in the detector. So it means that we need to amplify that signal. So the electron will be drifted, but now we need a nice way to proportionally amplify that signal. And one nice trick about double phase Xenon TPCs is that now when the drifting electrons reach the surface of the liquid, we can apply a second electric field that will extract them through the gas. And in the gas, they will produce electroluminescence, proportional secondary electroluminescence. So now we have another signal, but now bigger than S1. This we call S2. And because the signal can be amplified, our threshold can be made very low. Now, the combination of S1 and S2 is telling us, okay, we have salt trigger, okay, we have low threshold, and by measuring in time the distance between S1 and S2, now we have, again, the longitudinal coordinate. And by looking at the position of the optical detectors, we have now the XY position. So we can fiducialize the event. We can find in 3 dimensions where the event is. Now, the last requirement is that we know for sure that radioactivity will be all over the place, and we need to shield against this radioactivity. Now, liquid xenon happens to be an extraordinary calorimeter, and in fact, calorimeters of liquid xenon has been made in the past. So what you do now is that you want to build a big detector so that you go to the center, to the core of the detector, you use the rest of the detector as a shield, and you look at the very quiet core of the detector to look for the signal. So as you can see, liquid xenon is almost perfect detector for dark matter. There is another condition that you're gonna need to meet. As you search and you don't find anything, you will want to make your detector bigger and bigger. And scalability is a must. And nothing scales better than a volume. Because when you have a big volume of things, then you just multiply double, you double the longitudinal coordinates and the volume multiplies by 10. So this explanation, the reason why the liquid xenon is so good, explains why we have such a proliferation of double phase gas TPCs in the business of dark matter searches. The whole story started about 15 years ago with Elena Aprile and her group, and they put together the super successful Xenon 10 detector, which was a small little detector. And this small little detector already make a change of paradigm in dark matter searches. After Xenon 10, they built Xenon 100. After Xenon 100, they built Xenon 1 ton. After Xenon 1 ton, they built Xenon N ton. And meanwhile, another bunch of cousins pop up. And we also have Lux, LC, and Panda X. So in total, we have close to 10 dual phase Xenon TPCs around in the world. And you could ask yourself the question, they are all the same. They are all the kind of picture that I showed you in the previous slides, same principle of behavior. Now, the question that you could ask yourself is, do we need so many? Could we do with less? So let's examine that question. First of all, let me very briefly describe the search for the known unknown. So the known unknown, as I said before, are WIMPs. These are the kind of things, our favorite hypothesis for something that we really don't know what it's about. So dark matter could be made of WIMPs. And if it could be made of WIMPs, we can search whether we find those WIMPs in terms of the WIMP mass and in terms of the WIMP cross-section. And in the left plot of this slide, you can see how the different experiments in friendly competition, they have been excluding and excluding and excluding parameter space. And of course, we physicists tend to explain this tale like a sort of race. And here you see the Lux curve, and then the Panda curve, and then the Xenon 1 ton curve. In reality, there is no race here. In reality, there is a concerned effort to exclude or to discover. And this effort, this joint effort, has resulted in pushing really very hard the hypothesis of WIMP. WIMPs could still be there. There is still plenty of room to exclude them or to find them. But our favorite hypothesis, our favorite known unknown, is no longer so favorite because we really don't find it after a while. But meanwhile, we have really found that the technology is wonderful. The technology has increased the sensitivity by 4 orders of magnitude in 15 years. The mass of the detectors has been increased by a factor 200, and the background has been reduced by a factor 5,000. So indeed, we have learned a thing or two about Xenon TPCs in dark matter. Now, here comes the unknown unknown. So you're searching for something else, WIMPs. And all of a sudden, you start to look at the electronic background, at the electronic signal in the recoils, which actually is a background. But then you find that at very low energy, at 5 kV, you have an excess that is not consistent at all with your best guess of the backgrounds that you have in the detector. So what is this? The answer is we don't know. The answer is that it could be axions, it could be magnetic moment of neutrino, or it could be a background. A bit of tritium would do the trick and could give you this signal. The Xenon 1 ton people who have done this pretty analysis, they have no clue that they have any tritium in the detector, but it could be there. And now it comes the answer. Why do you need to have LAX, LC, Panda X, all these other detectors? Because all these other detectors will make independent measurements. And those independent measurements will confirm or refute this finding of Xenon 1 ton. And this is one of the crucial ideas that you need to keep when you are doing rare searches. You cannot rely on a single experiment because when it comes to describe what we know that we don't know, it's easy. But when we find something that we don't understand, we need more than one pair of eyes looking at the problem. So as I told you, time projection chambers, TPCs, are machines that allows us to move in time. So let's move in time to the future. The future is called Darwin, and it's a TPC which is 2.6 by 2.6 meters. So notice that it's slightly bigger than the original PerFET TPC. So 50 years later, we are almost back at the beginning, at least in what concerns to sizes. But it will contain nothing less than 50 tons of liquid xenon, and it will really allow to keep pushing the field forward. and to increase our chances of a discovery. So that was my first research. Let me move to the second possibility, which is actually my own field. The question whether the neutrino is its own antiparticle. It could be, because neutrinos have no electric charge, so there is no fundamental symmetry which is violated if you reverse all the charges of the neutrino. And so it is in principle permitted that the neutrino is its own antiparticle, and not only permitted, it is very interesting, because if the primitive universe contained Majorana neutrinos, which are their own antiparticle, and there was CP violation in the primitive universe, then we could come up with a very simple equation for the universe, which is Majorana neutrinos plus CP violation explains why we have a universe at all, and why in this universe there is no antimatter. Now, how do you actually demonstrate that the neutrino is its own antiparticle? You do it by playing a curious game called Double or Nothing. This is a well-known game in casinos. You put your money. If you hit the right number, you get twice as much money. If you don't, you lose everything. So people like me who do rare searches put their own careers on the stake. You go for 20 years underground, and then you either make a discovery or an exclusion plot. So it's a pretty risky game, but also Double or Nothing suggests the name of double beta decay. Double beta decay actually is nothing but a standard second order in Fermi constant decay. An isotope, as you can see in the left, like xenon 136, which is 10% of all the natural xenon, is stable. It will not decay beta to cesium or to lanthanum because it has less bonding energy than them, but it could decay by an oddity of nuclear physics in second order 236 barium. And this decay actually is standard. It's extremely slow. So the lifetime of the normal conventional double beta decay is 10 to 21 years. So stable for all practical purposes. It has been measured. Actually, we do measure it with a lot of precision. And it's interesting, but otherwise that's it, right? There is a bunch of such isotopes that decay double beta, and some of them are particularly interesting because they have high energy. They have a decay energy which is sufficiently high to suppress, to be above most of the limit of natural radioactivity. But what is interesting about double beta is not the decay, the normal conventional decay, but the neutrino-less double beta decay. If you do observe an event in which you only emit 2 electrons and no neutrinos, then new physics is at play. Now, how do you know actually that you have 2 electrons and no neutrinos? Because you're not going to measure the neutrinos in any case. Well, you do know, because if it is a neutrino-less double beta decay, the 2 electrons in the event have always the same kinetic energy. And so it's telling you that something weird is going on. And what is this something weird? This something weird is necessarily a Majorana particle-mediated interaction. The simplest possibility is that you just have a conventional light neutrino flipping. It's a spin. And in that case, you connect the inverse of the lifetime of the decay to the square of the effective mass of the neutrinos. It is an effective mass because all the 3 flavors of neutrinos circulate through that loop. But for all practical purposes, let's talk about the neutrino mass. So what the inverse of your period is proportional to the square of the neutrino mass and to a few other terms which are describe the nuclear physics involved. What is critical here is the fact that if the neutrino mass is very small, as it is, then your lifetime increases and increases and increasing because it goes with a damn square. And this square makes our life very difficult. So when it comes to xenon, so before I talk to xenon, let me give you a feeling of why this thing is difficult. As I said, the lifetime is related to the square of the neutrino mass. Because of the neutrino mass is known, and we know it is very small. And we know that this lifetime is going to be very long. Actually, we know that experimentally is already longer than 10 to the 26 years. And we have reasons to suspect that it could be as long as 10 to 28 years, even longer. Now, the radioactivity, what is the background of this kind of stuff? I'm looking for a couple of electrons in my detector and nothing else. What can give me a couple of electrons or a bit of electromagnetic energy deposition? Radioactivity, natural radioactivity. And what is the lifetime of natural radioactivity? 10 to the 10 years. So there is 18 orders of magnitude between the main background and the signal. Now, what is that? What it means, 18 orders of magnitude? Well, consider, so consider a beach of about 70 kilometers long and 10 kilometers wide. That will have about 10 to the 18 grains of sand. So what we are proposing is to find a particular grain of sand. Let me call it a blue grain of sand in the middle of a huge, enormous beach. So why xenon is of help here? So the first reason is that xenon is a very decent neutrino double beta decay. For a number of reasons, it has a relatively high nuclear matrix element, a good Q beta beta, a good phase space. So it's a good candidate for neutrino double beta decay searches. The other nice thing about xenon is that it's easy to enrich in xenon 136, because xenon 136 is the heaviest of all the isotopes. So in a centrifuge, you can make it easier. So it's the cheapest of all the isotopes for neutrino double beta decay. The proof of that is that actually there is currently in the world more than 1 ton of enriched xenon, and there is nothing of that sort in any other isotope. So it's a good candidate. Now, the other thing you need is a good way to separate the signal from the background. So one nice thing about xenon is that you can get good energy resolution. We will discuss that in a second. Or you could get a lot of self-shielding, protecting yourself against background. And that leads us to actually 2 possibilities to play in the game of neutrino double beta decay with xenon TPCs. One possibility is going to liquid xenon TPCs. We have already seen what liquid xenon. Now, the principle of operation is the same for both. You will get primary scintillation, you get S1, then you amplify your signal, you get S2, and then you use time and position of your sensors to get 3D position. The difference are what? In the case of the liquid xenon TPC, your energy resolution is good, but not terrific. It's of the order of 2% in the best case. And the best resolution, to give you an example of the best detectors in the business, which are germanium crystal, 0.2%. So you are an order of magnitude worse than the best guys in energy resolution. So you're not going to be all that competitive when it comes to energy resolution to suppress your background. But in exchange, you can do the same trick that dark matter experiments do. You can build a very large detector and look at the very quiet center of the detector. On the other hand, if you want to try high pressure xenon TPCs, you're going to have, and I will demonstrate that in a second, very good energy resolution, not as good as germanium detectors, but much better than the liquid xenon. And you can reconstruct actually the 2 electrons, which you cannot do in liquid xenon. In liquid xenon, you just see a ball of energy. In high pressure xenon gas, you really see that you have 2 electrons. So you have a very nice way of pushing backgrounds apart, but in exchange, you don't have self-shielding. Now, the other big difference is that with liquid xenon, you can scale up your detector. You can make very quickly, you can put many tons in a compact detector. With high pressure xenon gas, the detectors are bigger, and you need maybe to make many modules or several modules. But this also plays the other way around, in the sense that if you happen to have 300 kilograms of xenon, you can make a high pressure xenon detector. Not so easy to make a liquid xenon detector, because for scalability, you need self-shielding, and you need the detectors to be very big. So let me give you a description of the state of the art. So the first liquid xenon detector for neutrino double beta decay was the XO200 detector, which demonstrated the technology and actually demonstrated that they could get a very low background in the search, which was of the order of 10 to minus 3 kilograms per GRM per kb. Now, this is remarkable because the liquid xenon TPC, the XO200, was a relatively small TPC. What do I mean with that? I mean the following. This is the proposal for the successor of XO200, which is called NEXO. And NEXO is a detector which is proposed to have 5-ton mass. So it will be a detector of the, as large as xenon n-ton, smaller than Darwin, but larger than the large detector that we have now, for that matter. If you look at the left plot on the circles there, you can see all the game of cell shielding. If you make a detector, the red line is the attenuation length of a 2.5 MeV gamma, which is your main background. A 2.5 MeV gamma is going to penetrate the detector and it's going to make an electron and it's going to trick you. So you want to get rid of it. If you try to build a very small detector of 5 kilograms, the gamma is almost as long. The penetration of the gamma is as long as the detector, so no self-shielding. If you build a detector of 150 kilograms, and that was the original XO200 detector, you still have plenty of gammas hitting you. Now, if you go to a 5-ton detector, now the gamma is small. The gamma path length is small compared with the detector. Now you go to your central region, and the central 2 tons of your detector are going to be very quiet. And this is why NEXO expects to have a background rate which is of the order of 10 to the minus 6 compared to 10 to the minus 3 in XO200. So this is 3 orders of magnitude reduction. It gives you like 1 or 2 events of background a year in such a huge detector. It seems unbelievable, but the principle is totally sound. It's the fact that you go to the central part of the detector and you let your detector shield everybody else. So the proposed, yes.
Not 5 minutes, please.
Yes, the proposed XO detector will be will reach 10 to 28 years. And now let me move on to what high pressure xenon can do. This is the next detector that was proposed actually by Dave Nygren, myself, and James White 10 years ago. This is the next program where we are basically following the same steps that were followed by the xenon family. So we built a detector of 10 kilograms, then another detector of 100 kilograms, then we go for ton scale. This is our current detector, which is the Xenon 10 kind of thing, next white, where we have actually shown the full technology and actually demonstrated both energy resolution at the level 0.8% for with maximum, and the reconstruction of 2 electrons. See those pretty 2 electron tracks? These are data, not Monte Carlo events, and they correspond to our 2 neutrino analysis candidate. But perhaps the most important thing that we have found with the next program is again the unknown. When we did propose 10 years ago the next experiment, we thought that the main assets that we had was energy resolution and topology. And now we think that our best assets may be our capability of detecting the baryon cation produced in the neutrino-less beta decay. So the 136 baryon, which is doubly charged, it was known for a while that if you could detect this, then you could have a zero background experiment. But only about 2 to 3 years ago, we realized that there is a practical way to implement this in a high-pressure xenon TPC. We can plant into the cathode a monolayer of molecular indicators, as you can see in the pictures. Those molecular indicators are linked to the cathode. They have a fluorophore that will respond to whether you have captured or not a cation where. And in particular, we have been studying for 2 or 3 years this thing. And one of the prettiest things that we have developed on my own group in San Sebastian are molecules that without the cation, when you excite these molecules with ultraviolet light, they will respond in green, they will shine in green. But if they capture the baryon 2+ and then you excite the molecules, they will shine in blue. And actually, you can see here the example. What you can see on the top right plot is a green response of a layer of FBI molecules that we have developed without barium. Then we put them in an evaporator. We sublimate barium perchlorate. We chelate all the molecules basically with barium, and then we take another picture and see what you get. It's all blue. So this has opened the possibility of turning our next 100 detector that we are commissioning this year into something slightly different of what we thought it would be. We thought next 100 could be a detector with energy resolution and topology. And now we think it's going to be a detector capable of actually detecting the barium 2+ emitted in coincidence with the 2 electrons. And this, if we can demonstrate that, and by the way, we got a very substantial funding through the Synergy program of ESC for this demonstrator. If we can really demonstrate that, then we are essentially finding a recipe for a totally background-free neutrino-less double beta decay that could be extrapolated to ton scales. And actually, we propose to build a detector which is the same size as Darwin and almost the same size as the original PerFET TPC. So back to the future, as I told you, these devices are good to move in time. So to conclude, at almost 50 years old, the time projection machine invented by Dave Nygren has become an ubiquitous detector in particle physics experiment. Xenon TPCs have become major players in the search for rare events. Both liquid xenon and high pressure xenon TPCs are of great interest. And as I have tried to convey the impression to you, rare searches, both in the physics and in detector design, are interested not for what we know that we don't know, but for what we don't know that we don't know, and may bring us to surprise. Thank you very much.
Fantastic. Thank you so much for this scintillating and motivating talk with so much of promise, both for physics as well as for myriad of societal applications. I'm sure many people in the audience want to ask you questions. Let me quickly check if there are hands raised. I don't see, but maybe I can get started and while people are still thinking. So my question is about first of all, the cost of xenon. Let's go there and then we come later other questions of distortions and errors that you might have in the DPC. So these are two different questions.
So again, can you repeat the question to me?
So the first question is for the cost of xenon. How does this
compare? Okay, so the cost of xenon is a funny thing, because xenon is you produce xenon. You don't have factories of xenon. You have factories of air, and the cost of xenon is associated to typically how much your steel factories need air. The more steel you produce, the more air you need to filter, the more xenon you produce. And so it comes out that xenon varies wildly, not as a function of the market of xenon, but as a function of the market of other things. Instead, it's not that expensive. Typically, the cost of xenon, when the market is good, is about $3 or €3 per gram. And otherwise, it can go to 3.5. But the production of xenon has increased by almost an order of magnitude over the last decade or so. So it's a commodity that it's becoming more and more common. And so it is okay, we're going to have enough xenon in the world to do our experiments. The other thing is the enriched xenon. Enriched xenon is typically an order of magnitude more expensive, but other isotopes are 2 orders of magnitude more expensive than the normal thing. So in a way, the cost of enriched xenon is dominated by the people who can enrich with centrifuges, which is typically the Russians, but this is also changing.
Thank you. Professor Mondal?
Yeah, I think I have a question. For your two-phase, the dual-phase detector Xenon, what is the amplification you are getting at the gaseous phase?
The gain.
The gain.
the gain on the EL detectors. So it changes a little bit depending on your conditions. Typically in NEXT, we get about 1,000 photons per electron. In two-phase dark matter experiment is a little bit less because the electric fields are one of the pains of this field of this technology. Few hundred electrons per.
So are these LEM type of detector or what?
What?
This is what is this? What is the amplification you get it? That is the LEM?
No, we use typically we use for to produce this amplification. It's enough to get a couple of grids, and you will just get the amplification. You could use LEMs if you want. You could use GEMS, but most of what we have done always has been just simple 2 grids and let the electroluminescence do the work for you, and then we read things out either with photomultipliers with the silicon PMs.
Now, the reason I'm asking you question actually because it says the protodune double phase is having problem with this amplification, so I was trying to find out what is the real cause.
Yes, protodune is probably, well, it's a long story, but this is notice the highs. I mean, the EL amplification is known to work. This is no prototype. I mean, there is 10 detectors working today with EL amplification in dark matter, of course. So we know that to some reasonable size and electric fields, and when I say reasonable size, I mean 2 meters by 2 meters, it will work. Now, protodune is a completely different game. It's a huge detectors. In there, they have issues, of course. I don't think there are unsolvable issues. It's just that the electric fields involved are pretty difficult. I do believe that the technology of liquid xenon TPCs, double phase, single phase is a different game. Double phase can be extrapolated probably to Darwin size, order 3 meters by 3 meters, but no more. I mean, then it becomes really hard.
Thank you. Let's move to the next question. Rajendra, you have a question?
Yeah, yes, ma'am. Thank you. Thank you to the speaker for the very beautiful talk. I have a question that here you covered on xenon detector and liquid xenon detector, but there are also another candidate liquid argon detector that is also used by many collaboration. So what is the difference in terms of, let's say, advantage or disadvantage, maybe in terms of cost or also physics point of view or technology, how they are different and which is the which could be the best choice in that sense?
So argon, when you compare argon and xenon, there is a long answer and a short answer. The short answer is you should do both, actually. The reason being that if you are only looking for WIMPs, remember the known unknown, then you say, oh, let me just go for xenon because xenon has an atomic number which is much larger than argon, and therefore, it's going to be much better to search for WIMPs with xenon. But be careful because dark matter could be something else, not A squared, not WIMPs. And so argon has interesting properties that could, for instance, for scalar isospin, for other kind of nucleus could be very interesting to have argon. The second thing is that argon has advantages and disadvantages. The advantages of argon is that the structure of S1 signal, which has 2 time components, is so strong that you have a huge handle experimentally to say this is electromagnetic or nuclear recoil by just looking at S1. This is really powerful. The disadvantage is that argon has argon-39. It has a radioactive isotope there, and it's all the time giving you signal. So for dark matter, you cannot use regular argon as we use regular xenon. You need to deplete this argon from argon-39. So it's a combination. The answer to do is that for sure we need to and we will do both experiments. Otherwise, they are pretty similar. They are same idea. You drift electrons, you will amplify the signal, you will use the very same kind of stuff. They look also. And the dark side detector is also going for many tons. So basically, it's a similar game.
Thank you very much. I'm afraid that we will have to cut the questions now because we are getting late for the next speaker and the session is 5 minutes overdue. So So please move to the Slack channel for those who do have questions, and Professor Juan is going to answer their questions. And thank you once again, Professor Juan. Thank you.
Thank you very much. It has been a real pleasure to be here with you guys.
Yes. So now let's move on to another challenging and very complex system of detection, which is silicon-based. It is a very futuristic system, as you have seen in the abstract, which is probably going to show a wild promise for the future systems, which are going to be much large, based on sensors that are extremely sophisticated. And of course, we will learn that R&Ds which last for 30 years, what kind of things they can produce, both in terms of physics and in terms of industrial spin-off, and in terms of managing this whole project. So Heinz, the floor is yours.
Thanks very much for the introduction. Let me share this slide. Can you see the slide?
Yes, we can. Please go ahead. Thank you.
So I go to full screen. So over the next 40 minutes or so, I would like to give you a bit of an overview of silicon detectors. But silicon detectors is, of course, a huge field. So I focus it a little bit on to the tracking technologies. And I would like to show you where we are right now in terms of construction, the construction for the next generation, but then also give you some overview of ideas that are around where people currently really work on with a lot of creativity to make the next generation of detectors for really experiments in the very future, PPEE collision experiments. Good, to start. So where do we stand now? I guess you know all of that. We're right in the middle of LS2, and we're going to work now in parallel to the next run of physics data, taking also on the construction of the detectors for what is called the phase 2 upgrade. So this is essentially from 2027 onwards, where LHC, high Lumi LHC, wants to collect per experiment about approximately 4,000 inverse femtobarn. Now this means about tenfold the luminosity of what happens now. And this in turn means that we have major challenges ahead for the detector itself. I tried to put this in one picture, all the challenges in one picture, which essentially means from going, it's not quite as few tracks as you see here, but from very few tracks to a lot of tracks in the same time. And this means our detectors need more and more higher hit rate capability. You want to have small pixels. Because of the high luminosity, they really need to be radiation hard. And because we want to have better and better resolution, we want to have lighter detectors. And all that with larger detectors, hopefully for not too much money. So in the current works for high Lumi LHC, this is roughly the picture that we have in terms of radiation. And this is what actually drives a lot of the developments that we need now for multiple silicon detectors, semiconductor detectors, diamond as well. One is the bunch crossing rate of 25 nanoseconds, which sets essentially a time limit on the electronics. And the other one is the trigger rate, which sort of goes around 1 megahertz, trigger rate both in Atlas and CMS. And this sets the complexity of the entire readout system, starting inside the front-end ASIC, but running all the way through the data handling down to the analysis. And in terms of detector construction, this means multiple level of radiation hardness. In the innermost layers, you really have to go down to up to 1 gigarad of TID and maybe up to 10 to the 16 neutron equivalent per square centimeter. And then the further you go out, say 30 centimeters, you really go down by an order of magnitude. Now, if you look a little bit beyond high Lumi LHC and consider the future circular collider, so this is a sort of a sketch animation of a general purpose detector, how it could look like for FCCHH. This will have not only a super impressive colorimeter, but also in the very center, a very, very large silicon detector as a tracker. So this is sort of in first strawman's layout for a possible tracker at FCCHH. And this detector, the main point I want to make here is 30 meters long, 3 meters in diameter, and has 1,000 square meters of silicon detector. So it's not only a question of making super high performance detectors, it's also making a question of a lot of them, meaning reducing the costs. So in the development of the detectors right now, we focus also on making detectors easier to construct, working a lot together with companies and really trying to make them accessible. Good, but of course it's not all PP. It's also, there are a lot of activities, in particular now, a lot of activities for electron colliders. Just to mention a few, just to mention essentially the main big ones here with both CLIC, FCC, EE, but also of course the ILC, as well as the CPC, and all of them have silicon detectors in their center, essentially as the basic tracking technology. There the focus is of course not radiation hardness, but to be as light as possible, as thin as possible, and we try to push the boundaries, in particular on those type of tracking systems, to maybe down of 0.1% of radiation length for a single layer of tracking detector. Okay, so I would like to go through all this big host of semiconductor detectors in a set of slices. I will start off with hybrid pixel detectors, then move on to timing detectors based on silicon, and then go into monolithic CMOS detectors, and then to diamonds. So hybrid pixel sensors, they are the main workhorse for most of the vertexing systems for LHC. In the future, they will continue to play a very big role because they allow to have a very complex readout architecture in dedicated chips. Now we work with 65 nanometer processes. There's some R&D work going on already in 28 nanometer processes, which allow a lot of complex electronics. On the sensors, you can optimize them as a separate process, and there, what I believe will be their future application is very high time resolution, very high radiation environments. So maybe not the huge surfaces, but the very tough applications. Both in Atlas and CMS, of course, we use them extensively. They're in the center, essentially. And in the case of Atlas as a 5-layer pixel system, in the case of CMS as a 3-layer pixel system, the requirements for them are quite similar. So for that reason, Atlas and CMS, essentially the pixel experts found themselves together for the development of the front-end chip in the Odisha collaboration. This is a common development collaboration that will serve both the Atlas and CMS experiment for the next pixel detector. And currently we hold on what we call the Odisha chip. So this is the first full-size implementation of the chip. And this is the main workhorse for Atlas and CMS hybrid detectors. So we did get this first full-size detector back, which is called Odisha or in the Atlas jargon, ITK PIX V1. And that beyond one bug, actually, with one of the memories, it shows a very good performance. So what you see here is essentially a sort of a first menu of test results that were taken from the Odisha tests by the collaboration, assessing the analog performance, the digital performance, and this looks actually quite good. So it seems to be a very good workhorse for the future. We'll go into the next iteration next year, and this will be the basis of both Atlas and CMS for the next pixel chip. The detectors for that, so most of them will be planar detectors, planar NMP detectors, both for costs as well as high radiation performance. And in the innermost layers, Atlas has already decided to take 3D detectors. So 3D detectors means that you have, instead of having a flat electrode on the surface, you have the electrode going through the bulk. This helps for the charge collection, this helps for the radiation hardness, and currently we hold it approximately 2 × 10⁻16 is a good number to take away in the development of those detectors for the innermost layer. So they will be only used in the very innermost layer. Another detector that is getting together now and which has quite a novel actually readout system is the LHCb detector, in particular the Mesopix detector, which will stream data really at a very, very high speed. The main challenge for this detector is to work in a untriggered readout, where then the B reconstruction is essentially the triggering for the B reconstruction is done on the readout system on the outside. This means this detector has to cope with an enormous data rate. It's based on the TimePicks 3 detector, TimePicks 3 chip originally, that Anthony has introduced before already. So that's sort of one of the many uses of the TimePicks family chips. In the case of LHCb, it's called the Mesopix. You can see it really ups all the main characteristics for data throughput by an order of magnitude current compared to the present TimePicks 3. And this was also the challenge of the detector construction. This detector is now ready and being assembled and will go into the pit during the shutdown. And this brings me to timing detectors. Maybe the LHCb detector is one of the first ones to use this really actively in the context of tracking, but in principle you have for all of the future silicon systems the question of, do you add timing to your tracking information? The main purpose is quite straightforward. Once you can't resolve multiple collisions in the single bunch crossing anymore by spatial information, you turn to the time information. And you can do this either by having a continuous layer of a single timing detector on the outside of your tracker, or by measuring the time information on each pixel. So obviously the second part is a bit harder, and at the moment the main effort goes also in the development of timing layers, which we'll come back to a bit later. The precision scales that we need is given here. For present high Lumi LHC in the timing layer, it's about 30 picoseconds. If you go to an LHCb upgrade, I believe I have this on the next slide, you could do already a lot of vertex separation with a 200 picoseconds time resolution. So that is not too far off to what some of the current systems can do. The basic principle is quite straightforward. So if you have multiple primary vertices, you have the problem of which secondary vertex belongs to which primary vertex, and you resolve that by the time information of the detector. Now, the TimePicks 4 would be already in the ballpark of what is needed in terms of time resolution, but the question is, of course, do you have a fine pitch pixel detector that can actually deliver the time resolution for that? And this is one of the main focus of the Timespot collaboration, which took a very neat idea actually and pushed, I would say, a bit the limits of silicon processing. So this is some R&D that is done together with FBK in Trento, where you take the basic principle of a 3D detector as you have the single column in the middle, but this gives you a circular cylindrical field, which is not really good for a time resolution. So you turn it into trenches and you aim at a parallel plate configuration, and that gives you a much better time resolution. And they have done this, they have produced the first prototypes, which you can see here, and there was recently a very nice presentation by Adriano showing that they achieved actually in this, with lab electronics obviously, a time resolution of 20 picoseconds on a pixel pitch that is compatible with the with, for example, TimePicks 4 chip. So I believe this is some really encouraging development. But the big workhorse right now for timing detectors on a silicon basis are low-gain avalanche detectors. So the principle here is that you rely on charge multiplication to have a large signal, and you rely on a parallel plate capacitor geometry essentially to have a homogeneous field. Those are the two main ingredients to achieve a high time resolution in pixel detectors, of course, in addition to a very good electronics. Both Atlas and CMS have this sort of timing layers now, in the case of CMS being called the MIP timing layer, in the case of the Atlas experiment called the high granularity timing detectors. Both will use LGAT detectors with a pixel pitch of around a millimeter and aiming for 30 picoseconds time resolution. One of the main development areas is, of course, radiation hardness of this detector. Once you have this gain layer is achieved by having a very or relatively high P implantation under the N electrode in a high resistivity P bulk. That type of boron doping produces a gain of maybe 100 when it's brand new, but this gain reduces quite a bit once you start irradiating it, simply because of the effect of the acceptor removal, which means you destroy your multiplication mechanism the more you irradiate it. So there was a lot of R&D done also by the XXIV collaboration to better understand this process of the acceptor removal and counteract it. And this is done essentially both through a defect engineering of this gain layer, of this P layer under the N implant, as well as understanding the mechanisms and studying the ideal field configurations first through TCAD and then trying to implement it actually in silico. So here you have an overview of results from the XXIV collaboration in terms of gain stability. So the plot on the left shows essentially the gain stability at the beginning of the irradiation and then going all the way up to 10 to the 15 and beyond. The requirements for Atlas and CMS are around 2 times 10 to the 15 to 3 times 10 to the 15. And while a standard boron diffusion doesn't really, standard boron doping doesn't really give you a lot of signal once you go significantly beyond 10 to the 15. There's some hope by adding carbon into the game actually that this stays at a high level. In parallel, there are also developments by having a deep gain layer, so deeper in the bulk, deeper than a few hundred nanometer, to have to actually counteract this process of acceptor removal. Good. So where are we with those detectors right now? Those detectors are approved, or they're at the level of the TDR. So they go through the LHCC approval process. And in the case of the CMS experiment, you see the LGAT detectors or high time resolution detector time resolution as measured in the lab on the top left, where the detectors achieve already in the order of 35 picoseconds time resolution. This is just a plain sensor, which matches quite nicely also the Atlas results. The detectors are generally produced by FPK, CNM, or Hamamatsu. Both experiments work with these 3 founders together on the development of those detectors. The next big step is, of course, to bring this into a system. And this is done actually with pixel chips, the ETIROG or the Altirog chip in the case of CMS and Atlas. And these are test paper results from the first assembled modules, where those modules fulfill the specifications of the experiments already with a time resolution that is somewhere in the order of 40 to 50 picoseconds. Good. So, and now I would like to move on to monolithic pixel detectors. Just a second, I went out to full screen. fortunately. So why monolithic detectors? Hybrid detectors are super nice for performance, but of course they have a couple of disadvantages. One of them, the bump bonding, costs, I would say, a medium-sized fortune. And that limits, of course, the square meters you can build. So Atlas is pushing the envelope now with 10 square meters in hybrid pixel detectors, but that's not a stroll in the park. Monolithic detectors, on the other hand, don't have the bump bonding. You have sensor plus radar electronics all in one. And this helps you also if you want to go thin. Thin meaning really low mass trackers. So this is very interesting both for heavy ions as well as E+ and minus collider experiments. On top of it, CMOS industry, all of you have a CMOS sensor in your phones. They're produced by the square kilometers, not our detectors, but for imaging processing sensors, and we can work with foundries that have a really high throughput. To give you an example of one of the medium-sized foundries that I talked to, they asked how much silicon detectors, all including strips, does Atlas and CMS need combined? And the answer was, is the throughput of one of their foundry lines in 1 week. So, of course, life is much more complicated than that. But if you think about very large detectors, monolithic detectors are probably a good guess. Where are we now? So this is, I tried to put a timeline here a little bit in terms of applications in collider experiments. It all started with the STAR experiment at REC, with the ultimate sensor in the very first, one of the big first monolithic applications in heavy ion physics. Now, of course, ALICE is the benchmark, the ALICE inner tracking system with a 10 square meter detector. And it's considered for click as well, in particular for the outer trackers. Now, in the context of R&D for the Atlas Pixel upgrade, we also had a collaboration, the Atlas CMOS Pixel collaboration, that looked at producing radiation-hard monolithic detectors. I come back to that later. So, and then, of course, if you talk about 1,000 square meters, you want to take a technology that is reasonably cheap. So there's a lot of interest now pretty across the community to see how far we can go with monolithic pixel sensors. So ALICE, the ALICE ITS, ITS2 as it's called, is really the benchmark experiment right now with the Alpide sensor. It is a 10 square meter detector in 7 layers that cover a rapidity range of roughly ±1. And this was constructed over the last several years and is now ready for installation. Actually, the detector is on the surface. It's been commissioned and completed on the surface and is going to, as time allows with COVID, going to be installed beginning of next year in the ALICE experiment at LHC. Now, while the detector is commissioned, ALICE thinks already about the next detector, next possible detector, and that is in the innermost layer. So for the innermost layer, of course, it would be super nice, in particular for whole jaw measurements, to have a detector that is seamlessly wrapped around the beam pipe and be as thin as possible. And this is exactly what the concept for the ITS3 is, to produce it on 300 millimeter wafers, so you can cut out the 25 to 25 centimeter detector, and then literally wrap it around the beam pipe, again in 3 layers. Now, this means to go to a finer pitch node size development, in this case a 65 nanometer development, and not only work in single reticle pixel tiles, but really stitch the sensor together. So the idea is to take, starting with the Alpide architecture, to put it to 65 nanometer, maybe make smaller pixels, and then scale up the process to stitched sensors. So that would be the first approach for a stitched sensor that could serve the ITS3. Similar developments are also now being used for the click experiment. At the click experiment, here the goal is electron plus minus collisions to be as light as possible. In this case, also quite fast, time resolution of 5 nanoseconds, and click had a quite extensive silicon R&D. I want to mention only, which included hybrid pixel detectors, all different sort of silicon detectors, but I want to single out one of them in the area of monolithic detectors, where they looked to gang pixels together, to large detector units. Excuse me, something went wrong. To larger pixels, 30 by 300 microns. And this did work actually quite well. And so this actually means that we now can produce very thin detectors with very high spatial resolution. And then depending on the experimental needs, actually make pixels of the size the experiment wants, but all with the same technology. And this means you can serve multiple areas of your detector essentially with one development chain. Given that these developments are not trivial, this is quite a practical promise for the future. A lot of development was done within actually a mix of Atlas and Click to optimize the field configurations for these detectors to allow an optimal charge collection. Why Atlas and why Click? In the case of Click, time resolution is important. In case of Atlas, the radiation hardness is important. And both means that you have to optimize actually the field for the best and fastest charge collection. Good. Now coming to radiation hard monolithic detectors. So, as I said before, ALICE is the starting point, but ALICE is not really radiation hard. There, the goal is 10 to the 13, whereas for outer layers of Atlas CMS pixel detectors, they need 10 to the 15 already. And if you go to the center, you're solidly in the 10 to the 16 game. Maps are not really thought for that. You have two basic problems. The first one is you don't deplete the full bulk. And that means as long as your detector relies on diffusion of the charges, of the ionization charges to your electrode, it spells trouble for radiation environments, because with radiation damage, you will lose the signal in the non-depleted area, making your detector essentially inefficient. The second problem is a bit more subtle. If you have a very high radiation, this means you have a lot of collisions. With a lot of collisions, you have a lot of digital activity. And that means you have to have a rather complex electronics inside the pixel. And present maps are not meant for that. They usually work with a handful or maybe double-digit number of transistors in the pixel, but nothing like what is being used now, for example, in Audi53. So this means we also need R&D on the readout architectures. And in the context of the Atlas developments, two different approaches were chosen to look at the monolithic detectors. One is to use large electrodes, as you see on the very left. So all the electronics sits inside the collection electrode, which makes the electrode relatively large, and the pitch is limited by that. But of course, it gives you a very good coverage of your pixel with the electrode, which means a very good charge collection. On the other hand, on a small electrode design, your electrode sits outside the electronics area. This means you have a small capacitance, which is very good. This is like the Alpine chip in ALICE. But of course, your charge collection is troublesome, because you may end up with low field regions in your pixel. And the name of the game was, in the large electrode designs, how to handle large capacitances, and in small electrode designs, how to achieve full charge collection. And this is what the Atlas collaboration worked on now for a number of years, and actually we'll show you a few results afterwards. Worked out very well. The basic ingredients are the same. You need a high resistivity wafer, because otherwise you can't deplete it. You need a high voltage process, because otherwise you can't deplete the bulk. And then for electronics need, you need multiple valves. Quadruple valves is a good thing to have. Atlas followed 3 development lines, actually with 3 different foundries, LFoundry, EMS, and TowerChess, and also implemented different readout architectures. And I want to flash a few results on there. So this is in the EMS process, what is called the HV-CMOS sensor, Atlas PIX1, where after irradiation, we have seen after 10 to the 15 a very good charge collection. This is with rather large pixels of 40 by 130. The second type that follows the same principle is large electrode designs with LFoundry in the CPIX and the Monopix detector. Again, here, the same picture, very good charge collection, very high efficiency of the irradiation. Of course, pixel size is in this case 50 by 250. This is a bit limiting for spatial resolution. So very good for the radiation hardness, but spatial resolution maybe not super ideal. With small electrode designs, this is what is pursued in the TowerChess process. You have a small electrode of only 3 microns and small pixels out of 30 microns. The problem is, as I mentioned before, the diffusion. And what we have developed together with the foundry is a process modification that implements an additional implantation layer, which allows us now to fully deplete the whole bulk. This is now implemented in the Malta sensor, which we're going to show you a few results from. So this was developed again in the context of the Atlas R&D in 2 different readout architectures, asynchronous, synchronous architectures. This is called Malta and Monopix chip, where the focus is really very high hit rate, capable of very high hit rates, very fast time response, and of course, radiation hardness beyond 10 to the 15. This was implemented after a number of iterations, now also not only on the epitaxial material, but on Tucholsky material. Now, that may sound as a small little technical detail, but the reality makes quite a difference. This allows you to deplete a larger volume than just 20 or 30 microns. And it needs some quite careful engineering of the implant structures. And of course, I mean, we are not at a level where we can deplete 300 microns, but maybe 100 microns is not completely off the scale. And this gives you a much better signal. And with a better signal, you can do a lot of nice things. So these are some results of the, in this case, the Malta chip, 36 by 36 microns pixels. You see 2 by 2 pixel areas here, which essentially shows full efficiency beyond 10 to the 2 times 10 to the 15. So this is quite good results, and we are going to push the envelope there a little bit more now. Something that came as a quite nice surprise once you move to Tucholsky and larger depleted volumes, you start hitting actually a sweet spot also in terms of time resolution. So now we work on time resolutions with these monolithic sensors with 30 microns pitch at less than 2 nanoseconds. That is comparable. Yeah.
Just to say that there are 5 minutes left. Thank you.
Thank you very much. Yes, I'm nearly done. So there you can achieve actually time resolutions that are in the ballpark of, for example, the TimePicks 3 chip in a monolithic sensor. Of course, it's not an X-ray. Having 100 micron silicon doesn't give you the same X-ray detection efficiency, obviously, like what Anthony presented before. But for other MIP type of tracking applications, it can be quite interesting. Actually, there are a number of groups already interested in using the Malta sensor for that. Good. So to wrap up as the last point, I want to move on to diamond detectors. Now, diamond detectors are a specialty to some extent as a large bandgap semiconductor detector, but they're also used quite a bit at LHC in the context of beam monitoring, actually. So both Atlas CMS and also Alice uses them as either beam conditions monitor, where you measure luminosity and background, or beam loss monitor. The detector element themselves are always based on CVD, on chemical vapor deposition diamonds, usually in the polycrystalline, in some cases as single crystals. The polycrystallines are usually a square centimeter large, and the single crystals are usually 5 by 5 millimeter. And this is now also being considered for the upgrade. It's not considered, it's actually proved. It's going on with the construction for the upgrade in Atlas and CMS as beam conditions monitor. The principle is a time of flight measurement. What is shown on the bottom right sketch here is you measure the time of flight left and right of the IP. And if the time difference between the two diamond stations is 0, you know it was a collision. And if it's the time of flight between the two stations, you know it was a beam up, an upstream background that probably came from a collisions with or scraping on the TAS, on the collimeters on both sides of the experiment. So in this way, you can actually measure the background that you have in experiment very close to the IP and distinguish it from PP collisions. So it's a simple detector that gives you a direct luminosity measurement and beam background. And the beam background you can use in your safety systems all the way up to an LHC beamer board. So this is actually what is done in both Atlas and CMS. And now, so far this used to be primarily planar diamond detectors, so 500 microns diamond bulk with electrodes on both sides and parallel plate capacitor. Now what has started over the last 3 to 4 years is to make 3D detectors in diamond. So the basic principle is similar to a 3D detector in silicon, but now you create these electrodes through the diamond bulk, actually through a femtosecond laser that turns your highly insulating diamond into a more resistive carbon, usually graphite or carbon-like diamond electrode. And this was implemented, as you can see here, by the RD42 collaboration into a pixel detector and then bump bonded onto the CMS pixel detector chip. And they have actually achieved really nice results with full efficiency in these new developments. Of course, if you use it at PP collisions, you want to understand the radiation hardness of diamond, and that's already a pretty long game. It turns out that the damage that you see in diamond is specific to species and energy ranges. So RD42 now went through a lot of measurements on multiple diamonds to measure the damage constants for different types of neutrons, protons, and particularly in case of protons of multiple energies. And it turns out that once you have for each species the correct damage constant, you can scale actually the damage as a measure through the mean free path quite nicely, which you can see on the right-hand side. Another important topic was rate dependence that in particular hit the CMS experiment previously. So there was a lot of engineering now, in particular on the electrode construction, on the surface preparations of the diamond to make sure that you don't have a rate dependent response of the detector, which would be of course very bad for a beam loss monitor. So in this case now, this seems to be quite well under control, and you see it's better to 2% up to tens of megahertz per square centimeter. Good, so this brings me now to the conclusion slide in the shape of picture. I believe silicon detectors or semiconductors in general do have quite a bright future. They certainly have a lot of applications. We need them for the tracking and vertexing in the innermost areas of tracking detectors, and I don't think there's much alternative. Now, very interesting is, of course, to merge tracking and timing, and I would put the benchmark out to 10 by 10 microns pixel with 10 picosecond timing. That definitely would be a dream for everybody who does pattern recognition at high Lumi LHC or beyond that. And then, of course, for applications at EE colliders, the ultra-thin detectors would be certainly a big development, a big step forward also for physics. So in that sense, I believe there's a lot of activities going on. I hope I could give you a bit of an overview of multiple areas. I'm sure I left out a lot of important and interesting developments. But I tried to be as broad as I could to range from silicon detectors to diamonds with timing in between. Thanks very much for your attention.
Thank you very much, Heinz. This was an eye-opener as well, I suppose, for many people who are not from the field. And I start getting worried that you are competing for large areas as well. So these detectors are in danger. But I see that there is so much of progress in the timing layers, thinning the detectors, radiation hardness, modifications at the industry, in the foundry.
Yeah.
This is amazing. So thank you very much. And I see that there are many, many questions. I will just stop my commentary here and take the questions. So please, Shyam Kumarji, could you ask your question?
Hello. It's a very nice talks. You covered all the new technologies existing for silicon and diamond. So I have one question. Can you compare in terms of time resolution and radiation hardness all the technology, so that we can have glimpse which one is currently the best among all the technology like CMOS, LGAT, and 3D sensors? Okay, thank you.
Okay, so, that's a little bit difficult, but I will try. I believe it depends very much. I start with spatial resolution. If you do need 10 micron spatial resolution, then the game on the time resolution is not that trivial. So time resolution, for example, if you take now the TimePicks 4 chip, which is in the order, certainly much better than 100 picoseconds time resolution, rather 40, I believe. That is an enormous complicated chip already now to measure the time. It has a lot of requirements on the power dissipation and cooling. So to achieve that one, this is maybe the benchmark together with something like the time spot detectors, where you have trenches and can achieve in small pixels 50 microns or 30 microns maybe on the overall system. Those sensors are very hard to produce. So if you tell me now you want to have 10 square meters, FPK will certainly be happy to take your orders, I guess. But you may need to wait for a while. So on the other hand, if you take, now I move to CMOS sensors, we currently hold on a level of, with the multi-chip, at a level of 10 to the 15 in radiation hardness, 10 micron spatial resolution, and say a nanosecond level time resolution. We're trying to push this now sub-nanosecond, but again, this will take at least a year. There, the question is, how do you maintain the time resolution when you go to either smaller pixels? You need a lot of electronics to measure the time. And how do you shape the field? That is not trivial in monolithic sensors. And this needs a lot of work with the foundry. So I think there in this case, having, I leave out SPAT detectors now on purpose, this needs quite a bit of development with foundries and by the community itself. But of course, this would give you then a very thin detector with very small pixels and potentially very high time resolution. So that is scalable. So that could be a dream. That's why I mentioned it in the middle of the summary slide. If you go and want to have 10 picoseconds, 20 picoseconds, 30 picoseconds time resolution right now, LGAT is certainly the go-to technology. That is 1 square millimeter pad size. Now, 1 square millimeter sounds bad, but actually for where it's used, it's totally sufficient. It sits behind the tracking system right now. And going to, I don't know, 100 microns pixel pitch does not make sense there. You have so much multiple scattering before. It doesn't give you a physics advantage. So I think LGATs are a perfect choice what's there right now as the timing layers in Atlas and CMS. So I try to give you 3 answers rather than one.
Thank you.
Okay, thank you. Thank you.
So, a very big question, and so I think I encourage you to reach out on the Slack channel and continue the discussion, Shyamji. Okay, because there are a couple of other questions. Vivekji, you had a question.
Yeah, my question is just short. This is related to the last thing that you mentioned, the diamond detectors. What is the present state of art of energy resolutions at low energies?
At low energies.
By low energies, I mean about 10 MeV or 20 MeV or something.
I need to think a little bit. So it is okay. I'm struggling to give you a number here, but I compare it to silicon. It's about a factor 3 better than what you can do in silicon. This is simply because of the ionization process. If you look at the full width of maximum of typical signal distributions in silicon, diamond is half to 1/3 of it.
Right.
Okay, thank you.
Let's move to Rajendra. You have a question, Mark?
Yes, thank you for very nice presentation. Can you please go to slide number 41? Maybe I missed it something. Yeah, so here, if I look for efficiency, then the third one, that is 95.4%. I mean, why it has so low efficiency compared to other two?
Because it was a preliminary data analysis. I showed you the plots that we have published already. So this was at the beginning. This analysis was half a year old. We have now actually the very same detector with a better data analysis is at 98%. At 2 × 10⁻⁵. On this detector, you can't get to 100% or 99.9%. So that is simply the state of the analysis in this case. We're going to publish the paper in January with the new results.
I have another question actually. If I talk about timing detector, then which technology is better?
Please mute whoever is not.
Yeah, if I talk about timing detector, then which technology is better? I mean, there is bump bond and also map. So which has advantage and which can be a good choice for timing development?
Currently for timing developments, the LGAT certainly lead in terms of time resolution. Monolithic detectors lead in terms of spatial resolution. So if your primary concern is spatial resolution, I would recommend MAPS. If your primary concern is time resolution, I would recommend LGATs.
Thank you. Next question quickly. Sorry, Rajendra. Pravinji.
Yeah, thank you. Hence, I have a small question. We do have these randomized scans as for the luminosity measurements. So in comparison with the CVD and the randomized scans, like which are more efficient, like for the luminosity measurements?
Sorry, I didn't quite get the question. Could you repeat, please?
Yeah, okay. We do have these randomized scans, like to measure this luminosity and integrated luminosity. So in comparison with the randomized scans, I mean, and the CVD, the detectors, like which are like more effective in terms of, I mean, quantitatively.
Okay, so
and
that goes a bit.
Yeah, please go ahead. Yeah.
That goes a bit into the operation actually of both Atlas and CMS. The diamond detectors are on before you switch on the pixel detector. The main goal of the diamond detector is to make sure that the environment is safe for the pixel detector to go on. So in that sense, you do the beam setup measurements that you mentioned with vernier scans, and so you do before you switch on the pixel detectors. The diamond detectors are quite robust in terms of operation. So you use them essentially as your first go-to. You have 4 stations either side, up, down, left, right, and you use them during the beam orbit scans. So it's not a question which is the better precision. It's simply a question of practical operation in this case.
Thank you.
I don't know if I answered your question. I hope I did.
I'll I'll write you an email.
Okay, thanks very much. Yes.
Okay, thank you for your answer.
So thank you. And I do not see any more hands here, but I encourage everyone to contact Heinz, or I'm sure that Heinz will be available in the Slack channel also for
Absolutely.
answer to questions, because as you see, there are so many of us the younger experimenters who want to learn and to understand how to create the bridges, so to speak, also with industry in India, because that's very important also for the ecosystem. As you see, these are very large projects. We start today and we see the fruit only 3 decades later. So it will be great that this session brings out a lot of fruit, perhaps, in our society as well. So thank you very much, all the speakers.
Thanks very much.
Yes, thank you. And thanks to everyone else also for being patient with the pitches, if any, which we had. Thank you. And
thanks very much.
Bye.
Thank you, Archana ji. Thank you, Anthony, Heinz, and Johan. And so we will, next sessions on online is at 5:30 Indian time.